Hi everyone, this is Lee Newton, and I'm back talking about this nightmare tree that I think is going to come through my roof. This time, we're going to use a different approach. We're going to use trig to find the height. In the last video, I used a small mirror to find the height of the tree. So what I did was I placed that mirror 40 feet away from the tree, then I backed up 2.5 feet until I saw the reflection of the top of the tree in the mirror. What this creates is similar triangles. In similar triangles, you can use proportions to solve for missing side lengths. So by using cross products, I'm going to go 5 1/3 times 40, and that's going to equal 2.5 times x. All I need to do at this point is solve this equation for x. The solution to this equation is going to be x equals 85 1/3 feet. So triangles have been around, well, forever. But they didn't really gain that much traction until the Egyptians started building their pyramids. The unit of measure that they used was actually called a cubit. It was a stick, and it was a measuring device that they handed out at the very beginning of the day and collected it at the end. And it was the measure from a man's elbow all the way up to the tip of his fingertips. Trigonometry translates to triangle measure. And so the study of right triangles, or any triangles, is a pretty big category. And so around 300 BC, astronomers and mathematicians, they turned to right triangles to gain a little bit more insight on how the relationship between the sun and the moon and the earth all related to each other in size as well as in distance. Euclid was a famous geometrist. He's actually known as the father of measurement, and he was one of the first to study right triangles and their angle measure in depth. One calculation that he studied was the ratio of side lengths in similar triangles compared to their angle measure. And so remember that a ratio is just a comparison of two different lengths. You'll see it as a divided by b, a dot dot b, or a to b. And so what he would do is he looked at this angle, and let's say it's 30 degrees, and then he took a look at the hypotenuse, which is the longest side, as well as the opposite side compared to the angle that we're looking at. And he looked at that as a ratio. He then looked at other triangles with an angle of 30 degrees. They're all similar, so it's just the same shape but different size. And then he calculated those ratios, the opposite over the hypotenuse. He found that it was always the same measure. To make sure it wasn't a fluke, he went and looked at other triangles with degrees of maybe 31 or 32 or 33 or 45. And he found that the ratio was always the same. It was unique because of the angle measure. And so he called that ratio, opposite over hypotenuse, sine, which now we abbreviate as SIN. So the real hero in this story might be the astronomer, mathematician, geographer known as Hipparchus. He was the guy that wrote all of these down. He documented all of the ratios for the angles in a triangle. But he didn't even stop there. He went and took a look at other ratios that involved the adjacent side. So by studying the ratios, they found that if you only have one side and one angle measure, or two side lengths, you can calculate everything else about the triangle, all the angles and all the side lengths. And the nice part is that all of these lists that Hipparchus made, they're actually accessible to us today, and they're in our calculators under the sine, cosine, and tangent button, which are found right in the middle of the calculator. And if you don't have a fancy calculator, take out your iPhone or your phone in general. And generally, if you take and you turn the screen sideways, you're going to see that it opens up a whole lot of possibilities. So the other ratios that Hipparchus studied had to do with the adjacent side. And the adjacent side is not the opposite or the hypotenuse, but it's the one that's kind of touching the angle. And so the cosine is the adjacent divided by the hypotenuse, and the tangent is the opposite divided by the adjacent. A lot of people remember this with the acronym SOHCAHTOA. Sine, opposite hypotenuse; cosine, adjacent hypotenuse; tangent, opposite adjacent. Let's take a look at an example. Let's say I'm in a helicopter 1,000 feet right above an island, and the angle of depression to a swimmer in need is 45 degrees. And what I want to find out is the distance that the rescue crew is going to have to make from the island to the swimmer. So the angle of depression and the angle of elevation in this case are going to be the same, because if you see, we've got parallel lines and those are going to be alternate interior. So they're going to be the same measure. So the angle I'm using is 45. I've got the opposite side and I'm using the adjacent side. So I'm looking O and A. O and A, I'm going to use the tangent ratio. So I'm going to set this up. Tangent of 45 equals opposite divided by adjacent. So from here, I'm going to put a 1 under the tangent of 45 because then it's easier for me to see how to solve this problem. Now it's a proportion and I can just use cross products to solve. So I'm going to go 1 times 1,000 and then divide by the tangent of 45. And just remember that the tangent of 45 is just a number. It's a ratio that Hippocrates calculated a long time ago. And now we can access it in our calculator. So we end up with an answer of 1,000 feet, which seems weird because that's also our altitude. But this is a very special triangle. It's a 45, 45, 90, and it's been studied quite a bit. And it's isosceles, and so both sides are the same, and the hypotenuse is actually the side length multiplied by the square root of 2. So let's go take a look at my nightmare tree. So the first thing I needed to do was I needed to get some side and angle measurements. So the way I found the angles was by making a clinometer. A clinometer is just a protractor with a straw and some tape, a string, and a little bit of weight. So when I tilt this clinometer up and down and I look through the viewing straw, it's going to measure an angle for me. So I stood 50 feet away from the tree and I took a look up through the viewing straw to the top of the tree. And what I found that it was 32 degrees. But remember that that angle is not the angle that I am from the tree. It's actually measuring the very top angle. So here we go. 50 feet from the tree, 32 degrees, and I am 64 inches tall. And so I changed that into feet by dividing by 12, so I get 5 1/3. So pause the video now and do the math. So the question was, how much of a difference is there in feet using trigonometry rather than similar triangles? The answer we got in similar triangles was a height of 85 1/3 feet. So using the angle of 32 and the opposite side of 50, we're going to be able to calculate the adjacent side using the tangent ratio. So I'm going to set it up. Tangent of 32 equals opposite over adjacent. Then what I'm going to do is throw a 1 underneath so I can make this into a proportion, and then I can cross multiply and divide. Once I get my answer, I need to add that 5 1/3 feet because that's the distance from my eye to the ground. So 80 plus 5 1/3 is 85 1/3 feet, which is the exact same thing we got with similar triangles. So look at that, the math really does work. So right triangles are pretty amazing. We get to use math, do less physical work. So a thought to leave you with. Did sine, cosine, and tangent ratios, were they invented by Hippocrates, Euclid, other astronomers and mathematicians? Or were they discovered? Because really, math is just the language of the natural world. So, next time, we're going to be talking about almighty Pythagoras and the Egyptian rope stretchers that are way older than he is. See you then.